So some people asked, some folks asked whether MPI is better than OpenMP or which is more performant. The answer is that it's a different ball game. With MPI, we are really going to use thousands of nodes and use the full bandwidth they have collectively to offer, the full amount of compute power they have, the full amount of network bandwidth, and the whole resources. So with MPI, we are really talking about extremely large scale computation that drives multiple machines in parallel. Within each machine, of course, the OpenMP mechanism participates in driving the course in parallel for you. So clearly, they are at a completely different scale. For solving large problems, you need a large number of nodes. No ifs and buts there. Single cores with their memory systems cannot handle that much volume of data or compute. That said, the equation of where to draw the boundary between MPI and OpenMP has been changing. In olden days, I think I mentioned this, but in olden days, people used to think there will be lots of simple nodes and multiple, maybe hundreds of thousands of them. But now the view is that with lesser nodes, with more capable shared memory nodes, with more shared memory parallelism inside, the extent of MPI ranks may not be more than 3,000 to 4,000, even in large supercomputers. It's good to trace the number of nodes in large supercomputers, MPI nodes, how many MPI ranks do they allocate, and see how the numbers are changing over time. That's one thing. Some people are also wondering about tasking, and I haven't given a satisfactory answer to the task mechanism in MPI. I think I will address that tomorrow when I discuss threading building blocks. But the advantage of tasking is that you don't start threads and keep them idle. Whereas with tasking, the mentality is you create work items, so-called work items, which are just a description of the work to be done, the computation to be done, the function to be executed, keep them in a task queue. Then the available thread pool can be fixed and they can do work stealing. So generally, task-based executions go with good runtimes, with work stealing. That balances the load overall. The other thing that I will continue with the code reading, since some of these came up. The other thing that everybody worries about is data movement. The less data you move, the better you are. Even within a chip, within one clock cycle, the amount of distance data travels within a chip is limited. So from one end of the chip to the other end, it takes several clock cycles for the data to go. The longer the data goes, the more energy you consume. So wires consume a lot of energy, charge and discharge wires. And all that is extremely, that's why GPUs have an extremely simple regular layout with extremely simple, nice looking, even geometrically nice looking cores, and they have short data movement and all that. With MPI, people are trying various other things to reduce data movement. With MPI, obviously you are moving more volume of data. So how can you still reduce data? So people are doing data compression. Data compression is getting extremely important. So there are very good floating point data compression libraries available from Lawrence Livermore Lab and other places. I know one library there. There is a scientist by the name of Peter Lindstrom who has developed floating point compression libraries at Livermore Labs. He has put out his libraries. The idea with that is that you can bind it to his libraries, and it does lossless or lossy compression, both. And when you use lossy compression, he tries to make the lossy compression behave well with respect to the science you are doing. So it doesn't bend shapes out of the norm and all that. So data compression is going to be useful. Data compression is one of these silent technologies that is creeping up. It's getting everywhere without people realizing it. And you can see how many floating point words will share. Maybe you have quite a few Mantis bits, right? So if you are doing as iterate, then the numbers you generate will differ very slightly in the low order bits. The higher order bits will be rock solid. So why ship the entire 32 or 64-bit quantity? So there are plenty of opportunities for data compression, and people are writing libraries. So the objective of the remainder of this lecture is to finish this reading and make sure that we understand the full code, at least to the extent I'm discussing, see the correlation with the ISP view, And then we will look at some other examples, MPI examples, and there are also these pretty pictures tend to illustrate the behavior quickly. I don't know which static. It's not coming. Okay, I don't know where it's coming from. Okay, okay. So Q sort. Okay, so Q sort is the local sort. It went to it didn't. Quick sort, and now if debug. Okay, so now this is the iteration. So the local sorting is done. Now the odd even dance begins. So for phase equal to 0 phase, then less than p phase plus plus. So the runtime, effective wall clock runtime across the given number of processors will be decided by p. Who decided p? P is the number of processors. It's my rank. So that's how it was passed in. So we are basically going to iterate over the number of ranks in the system. So the odd even iteration happens. So let us look at odd even iter and see what happens. So still no MPI commands. So let us look at odd even iter. So now we have this odd even exchanges, and okay, so the partners have been defined. We looked at odd partner may be missing or even partner may be missing, in which case we assume it's proc null. That's a common coding style. Then you can just silently receive from your odd partner or even partner. If that odd partner is a vacant space, that will be a no op. It won't cause any harm. So it's a good to protect the boundaries. And as you know, as you may know, in large scale computations, there is this phase called halo exchange, which is you may want to compute a little bit more than your current region of interest. The neighbor will compute a little bit more than their region of interest, and then once they update a little bit of your region, they update a little bit of your region, you update a little bit of their region, you exchange the halo cells. These are all details which prevents the boundary surprise and all that. But that's a detail which I don't get into. Phase odd, so this is the even phase, this is the odd phase. So if even partner greater than or equal to 0, which means not a proc null. I think that's what it reads. I really question the author not putting a comment there, because I know that proc null has an alias with -1. Did he mean that? I don't know. If I did not know that that is the case, I can't even take that guess that proc null is -1. That is kind of bad. But could be that. Okay, so send receive. Okay, send receive is a facility provided in MPI to finish a send and a receive. It's preferred, I guess, in some codes. ISP does not know send receive, I think. So it opens it into a send and a receive, I think. I need to check. So local A, local N, MPI int, even partner. So what is happening is the local, okay, so the basic picture at this point is I'm sending my data and I'm going to receive your data. That's the local exchanges that I showed in pictorial form. At the end of the MPI send receive, we need to do the merge high and merge low. So send receive is sitting in which line? The notion of line number is when it ends. I discovered that. So it's ending in line 320. So let us see which is sitting in line 320 here. That's not it, because these are the initial. Okay, these sends are not the these sends are not the initial. These are not the odd even. These are the locally generated random number. Okay, so this is the locally generated random number being shipped to the root rank. Then happens send and receive. So we are looking for line 330, line 20. This is line 320, and this is line 320. Happens to be the send receive. This is sending, that's receiving. So you can actually trace out the code lines out here. I wish we had brought out more arguments. Some arguments don't look that pretty. The nice, another nice view I would like to create. When I was preparing these lectures, I thought we should create another view where these arrows are superimposed on the source line. That would be nice, right? So when you step through the execution, the arrows between source lines should flip. This end is now talking to this, receiving this. When you step, the arrow should change. That would be a nice superimposition of the code and timeline view. That is a future project. All these are good undergraduate projects. If you have students interested in building simple graphical interfaces to help you parallel program, these could be good Java projects, or JavaScript is very common these days. There is a D3, DA3, I think, intelligent document. So anyway, so we located the send receive. So otherwise merge low. So then after the send receive, so this send receive is sitting for the odd base. Oh, sorry, this is 330. That's the send receive ending in line 330. We saw that also. Line 320, line 330. Line 320, line 330. Okay, so the send receives. Anyway, there is a way to associate. I don't want to overdo this. Then what happens? Then, okay, so once you get certain data, you can do merge high or merge low, depending on which rank you are. So, oops, sorry. So if you are a odd rank, then you are merging high. Makes kind of sense, because in the example at least, the odd is going to retain the high merged values, and the evens are retaining the low merged values. I think the static from my clothing. I discovered I'm wearing nylon pants, so it could be the clothing. Okay. Old electrical engineering comes in handy, you know. Okay. So this is send receive. Okay. So merge low, merge high has the actions. So all you need to see is send merge low, merge high, and odd even exchanges. So let's read merge low, merge high. Merge low is going to keep all the low values. You can see pretty much what it does. It's while my key of an index is less than equal to received keys, I'm going to keep, what am I doing? Temp, okay. So the receive my keys in the temp. So I'm building a temp of my keys. So we are keeping the keys that survive after the merging in the temp. And then once the items that survive in the merging phase are discovered, do a mem copy to my keys. Okay, that makes sense. It just is overwriting. That's all. Merge high is a similar routine. Okay, so after the merge low and merge high iterations, so that's odd evenator. Okay, that's it. So this is sort. So Q is, that's not sort. Okay, sort. Then what do? We are done. Print global list. That's it. So let us see what final MPI actions are in the print global list. MPI calls in that function. This is sometimes why MPI programs deadlock, because some of the MPI calls are buried 2-3 levels deep in a function. So if you wonder why your MPI program deadlocks, you didn't probably encounter the right number of barriers, but unfortunately the barriers are not in a single place right under your eye. It could be in different call paths in functions. I think it's a bad practice to write very badly obfuscated barriers deep here and there. Ideally it should be one line of code executed by multiple processes. That's more reassuring. CUDA comes to your rescue. Why? When you hear CUDA, if the instructor doesn't have enough time to talk about it, CUDA requires textual barriers. Have you heard of that? Textual barriers means it has to be a single barrier statement executed by all processes. You cannot have two different barrier statements in two different code paths coupling to be a barrier. In MPI, I can say, if I am rank 0, I go through this way and hit a MPI barrier. If I am rank 1, I go through this code path and hit a barrier. Those barriers will align and make progress. So MPI doesn't require textual barriers. That's why the code can be obfuscated. CUDA, unfortunately, will complain immediately. It's also designed that way because they want to not lose barrier resources. It's a very precious resource. A lot of reasons. So in CUDA, barriers are textual, and code reading will be more fun also. These are all coupled, right? I mean, the way you design the code has to be understood by humans, verified by humans, debugged by humans, then only you will get HPC. And so these are all side details that happens to be of importance. Okay, so print global list. My rank equal to 0. What is this doing? MPI gather, we studied that. Else also MPI gather. Why? Barriers are MPI gather is a collective or not? MPI gather is a collective. So else, if the else doesn't call MPI gather, we are in trouble. So MPI gather has to be called by all ranks, except rank 0 calling MPI gather means good stuff is going to come out of it, and we will print it. Yeah, exactly. That's exactly what I yeah. All of so if I don't have MPI gather here, it's a bad code. It'll die. It'll deadlock. Yeah. So oops. Okay. So MPI gather is expected in every code path, except this MPI gather is the one for the root rank, line 227, and this is 235. Line 227, line 235. Okay, so that's there. So you can see, I mean, this is reassuring that there's a, okay. So here the MPI gather will get all the data. The local data are all gathered, and we get the global list, which we print. Okay, I mean, this can be run also. Let us run MPICC. Where is it? Is it there? Which one? Oh, I see. Oh, okay, odd even. Okay. Oh, MPA. Yeah, that also is badly named. Yeah, I don't know why it got named like that. So let us run. This is it's only at 8, much like our lab machines. It's a 4-core hyper-threaded. It will be long printouts. I don't want that. G global N. Oh, it does not need the processes anyway, because it already knows from the N, the rank. Yeah, I mean, it does the obvious thing. Each rank has generated a random number, and then the global is sorted. Okay. Same thing will happen with ISPCC. Yeah, you can believe that. Okay. Okay, so what else to indicate? So now let us switch gear and study other MPA programs, and a lot of fun reads are there. What is this? Okay, so let's look at this program. This is a very small but a very interesting program. Some of you ran this also yesterday, I saw that. Numerical integration, trapezoidal integration done by multiple processes. So basically there's a function, you have to integrate the area under the function from some min to max range. So you divide the range, make MPA processes do the trapezoidal integration for the subranges and add up. That's the thing that is being done here. So init, com size, com rank. I won't go into all the details. We are deciding the b minus a by n, which is the number of trapezoids we are going to build. The number of trapezoids is calculated here, and yeah. Then it decides the length of each process's interval of integration is the local n times h. So h is the step size. So each process will have a local n, and the interval of integration is determined, etc. There are some calculations of this kind anyway. So they all then call trap and then integrate their trapezoidal regions under their area, under their bailiwick or charge. They have to integrate their own regions. And then my rank equal to 0, add up the integrals calculated by each of the processes. Otherwise, okay, so now you can see what is happening. All the processes other than rank 0 are going to send their integrals, and rank 0 is going to receive all the integrals and then totals up. I hope the structure of the MPA programs it's become more familiar to the eye now, okay? And then they print the results and shut down. So let us look at the picture. If you can get the picture quickly without any bugs, that is confirming. So nothing happens. They are all integrating and finding their integrals, and finally they are all sending their answers. The root rank is receiving the answers one by one and finalize. So that's, I run these so many times that when I look at these pictures, I think I know which code it is. It can be useful. Can we diff these two pictures? Can be, maybe. If you change the version of your code slightly, the code doesn't behave well. Can we diff these graphs? Maybe. And suddenly find where the graphs are different and start debugging there? I think so. MPA communication graphs are actually an item of interest. People are actually mining MPA communication graphs from large applications, and they're putting these into big graph databases. So those who want to work on big graph, big data, big graph, have a ready supply of graphs available. Just generate communication graphs through instrumentation. Then you can give it to your student, and then you can make them work on machine learning, similarity finding, Jacquard distance, and all that. So if you want to rope in students into HPC, if you are struggling, give them machine learning projects associated with HPC. Don't tell them it's HPC. Just start drawing them from the other end, and slowly, oh, now you code an MPI in Fortran, okay? Oops, after some time. So actually, some of my students are working on debugging. What we are doing is the following thing. So what we observe is that most programs spend almost all their time in loops. Do you agree? I mean, there is no program that needs to spend time running straight line code. Almost all programs have to be in a loop of some kind or the other. And loops are not that long. You don't write a loop that is 2,000 lines long. Loops are kind of 100, 200, etc. Okay. So suppose you can mine loops from programs. How do we mine loops from programs efficiently? This is the nature of the game, because these are all extremely long-running applications. We don't want to interfere with the runtime. So we use a tool called PIN. Have you heard of PIN? P-I-N, PIN? It's one of the best tools that Intel has given to the world. PowerPC doesn't have it, ARM doesn't have it, None of the other processor types have it. NVIDIA barely has a tool that barely works. Pin is a binary level instrumenter, so it actually tells you which binary instruction sequence is going. So and you can then do things with the instruction sequence. Like if you see an add, you can even substitute that add with your own other operation. Just insert. Extremely well maintained. So whenever processor generations advance, pin advances too. So what we do is we do pin collection of data from actual running processors. We are scaling it to thousands now. And when we collect data, we want to immediately compress it. Compression is important because all processors have memory hierarchies, like Cherian was saying yesterday. So L1, L2, L3. Okay, so the less volume of data you move through higher levels, the better it is. Up to L3, the same volume of data comes. As soon as it leaves L3, and in fact, yeah, the compressor is, we write a data compressor, my collaborator, not us. I have an active collaborator. He has trainable compressors. His specialty is to write extremely efficient data compressors based on the data patterns. So we bring out extremely compressed data. Its compression factors are pretty amazing. He does all kinds of tricks to get the function. So what we mine are call returns and mainly call returns and loop. And then okay, so that's what we mine. So sometimes function calls can be obtained. Function returns are non-standard returns. Sometimes you return from a program through non-standard paths. So you don't know where the stack top is. So he has a heuristic to correct the stack top. This is very detailed work. So once we get compressed traces, we start discovering loop structures. And there are classical algorithms in computer science to discover loop structures dating back to the 70s. So somehow we can construct a regular expression out of the program. You all know regular expressions, right? A star P. We can't get a star there. It could be A raised to 200,000, B raised to 10,000. Etc., etc. So we get something that looks like a regular expression. Then we are building a diffing tool for these executions. Hopefully we can find bugs that way. Because finding bugs is a really, really, really hard thing. Once you deploy, chances are, unless you have trained yourselves to be a very seasoned programmer with years of experience, which I haven't, but many of my students are, debugging is a very costly thing. Debugging costs a lot of time. In the hardware industry, 60 or 70% of processors, the development cost is debugging, 70 or more. In software, it's not documented, it's very high. So debugging can be done using graph diffing, can be done using compression, help by compression. Loop summarization is important. It's all the surrounding story to what I'm saying. With that, we finished numerical integration. Now we had to see some fun things in MPI. And I may not have too much else to talk about, so let's go through some of these. There is a command called probe in MPI. You may not need it always, but it's handy to have it. Probe says, a processor can probe and say, is there something for me to receive from processor 3, kind of a thing. Probe. Probe is a blocking call. There is an iProbe, which is a non-blocking call. iProbe can return, no, there is nothing to return. And it can, something like that. I forget some of the details between probe and iProbe. Let us look at it. Probe is like the I connotation. So MPI underscore probe. One is blocking, one is non-blocking. That much I'm clear. MPI probe. MPI probe. Source rank or any source. Status. Success. Everything. Blocking, test for a message. So is there a message to be received? It's a blocking call. So if there is a message to be received, at that point it will wake up and say yes. MPI probe. So probe and iProbe exist. iProbe is the lightest weight call, like I receive and I send. MPI probe behaves like MPI iProbe, except that it is a blocking call that returns only after a matching message has been found. So you should probe a process, that call will block till a matching message is found, then it returns. Then afterwards, if you do a receive, is it your obligation to receive from that process that you probed and found a message to be waiting? No. You might completely ignore that and receive from somebody else. So that option exists. These are interesting features. It's not very clear when you will need it. But let's look at a simple example and its run result. We found these things to be important to handle in a testing tool like ISP, so we made sure that it works for all constructs, whether it is used frequently or not. Because these constructs have tricky corner cases. We don't want to miss tricky corner cases. It's like the usual, right? I mean, a disaster doesn't strike that often. Does that mean you don't need to build the safety walls? No, you have to build safety walls. Whenever it strikes, you need it. So rare events are important. So switch my rank, MPI send, break. MPI probe, receive, receive. MPI send. So this is two processes attacking this guy in the middle with a send, that's all. And once this guy probes, who's he probing? This is interesting. MPI probe, any source. Is there anything for me to receive at all? I don't care who it is. That's what it says. Then I will receive from anybody, then I'll receive from anybody. Any source. How do we understand that? Look at its picture. So this has 4 executions. So here, that's one send. That got probed successfully by this red box. A red box means it's any source. That's how we color code it. And this is any source receive. So this any source receive also received from here. This happens to be any source. So this send got picked up. Is that the only one that exists? And if you run in an MPI system, maybe you'll see this pattern all the time. But if you change the speeds of networks or recompile, it might change to this. So you probed using any source here, but this receive picked up here, then this got picked up. That's 204. 304 is you probed this one, you received that one, then this received. 4th is that. You can teach combinatorics using this one, I guess. And it looks fun. Okay, so that's that. So finally, last but not least, we should do a matrix multiply. We were discussing the code yesterday. Let us go through the matrix multiply. I think that will be the time at which you have seen enough MPI and start believing we can all code. Okay, so this is interesting. These things are okay. There is a corresponding diagram for matrix multiply. Okay, so let's read a matrix multiply. Sorry? No, I'm sorry. I should show you something. You wanted to see which one? Yeah, probe. Okay, let's look at the code. So you saw the picture. Now we can see what the code was. So this is the send. This probed with any source. Then this can receive from that source or a different source. So the wildcard is useful occasionally, but wildcards can give you this non-deterministic. Exactly. Probe is only going to give you. Probe itself has the wildcard. So it says I could have successfully probed. I have a message received from here or here. But you're totally right. If I commented out the probe, this program will complete without deadlocks. But then the receive will show this non-determinism too. The first receive can pick up from 1, and second can pick up from 2, or vice versa. That can happen. And some of that non-determinism is useful, which you will see in the matrix multiply example. So let us try to see whether MPI matrix multiply 1.c has a bug, and the picture shows me that some sends and receives are orphaned. So this is a good opportunity for us to debug. I have not tried to do that, but let me just put it up, okay? I collected these logs. So when after some time, I don't believe in my comments. Sometimes I write a comment saying, this code has a deadlock, but I edit it. But in this case, the comments seem to match. Deadlock, yes. And I do see some orphan receives. All I can say is I have to spend a little bit of time seeing why this code deadlocked. But there is enough evidence saying how much it progressed before it hung. So that's another use of ISP. But let's not worry about this version. It was fixed in the second version, MM2. So matrix multiply 2 is what we will read, and we'll look at its diagram also. I think this is matrix multiply 2, but just to be sure, I'll kill all that. Yeah, those are all different. Okay. Okay, so let us see the algorithm was similar to what we explained yesterday. You have a certain number of rows, you have a B matrix. You broadcast the B matrix to everybody, and then you start sending the rows, and whenever the row got multiplied, you see who got multiplied it, and send that process more rows. So that's the algorithm. That is sort of reflected here. You can see that. The first thing we do is a bcast. Line 102 is a bcast, so the B matrix is being broadcast. And then root process 0 is going to send the rows. This is sending row, this is sending the row. You see, this is sending a row. So once it has sent the rows, it is now waiting for a reply to come back. Then it will send one more row here. Then receive the answer from here. Send the. It may be following a cyclic order to circulate the more rows. So this diagram is just cycling back more work till all the rows are multiplied. We have to now see the code. That's the general idea. We have to now see in the code where all these details appear, and then finalize. And this is written in a good style by some other authors in a tutorial, so I think it's pretty interesting code. So declare the A matrix, B matrix, and C matrix. So they're all the matrices to be A and B times A times B equal to C. We have some buffers. The usual start by now, init com size com rank. We take the rows, and if I'm the master, I create the matrices. I don't know why I have this comment. Then bcast. So the B matrix is being broadcast. B rows times B columns items are there, MPI float. So somebody asked about matrices. Yeah, we just flatten it and send it. Yeah. And now the rows of A are being sent. So for I equal to 0 to numproc minus 1, send the MPI send of the buffers of the rows. Yeah. Numprocs. Okay, this is a double thingy. Okay, less than numproc -1. That's nice. Good source of C bugs there already. Usually I equal to 0, I less than n is a nice pattern. This is I equal to 0, I less than n minus 1. Okay, so it is saving. It's only doing n minus 1. So the root process is not doing too much work. The root rank is happy sending work, receiving work, and circulating. I'm just looking at this code and saying how many ways in which somebody can screw up and make this code hang and get answers. Yeah. So this, I don't know. Programming guidelines should strictly prevent people from writing varieties. Yeah. But I think this is happening. I less than n minus 1. Okay, good. Then MPI sent. Okay, so the rows are being sent. So all the rows have been sent. Now what? Num received equal to 0 so far. Now for I equal to 0, I less than C, not crows, but C rows, I think. It is plus plus. MPI receive. Who should I receive from? Where is this? That's the one that tells me. Yeah, I think that's what is telling me the person I should receive from. So it's going through cyclically and receiving. Yeah, I forgot the argument position. Num received percent. Yeah, so num received is increased in this loop. So it is receiving step by step by step. Thank you. Num received. This is all bad. I would think this code has to be rewritten. If I wrote it, I should be blamed. Okay. It's a dangerous amount of mental complexity right here. Anything can be off by 1 and the code may not work, and you may be months before you find it. So I think strict programming guidelines are important. I'm told that an expert faculty colleagues of mine who write extremely good code, when they work with collaboration with Google and ask to submit their code, the Google engineers don't do it. Their code review process is so amazingly deep, they just make him do additional work. So I think industrial experience and industrial coding standards are highly important. For companies like Google, that's the only way they're surviving. HPC slightly lesser. So I've been told horror stories of HPC just because there is no company mandate to productize, I guess. Anyway, any tag is available. This is an interesting business. Any source and any tag. Tags form another matching option. So you can say, I want to receive from source 23 with the tag 35. So then I'm only sensitive to messages tag 35. So the send receive matches go along the tag lane as if there could be different tagged lanes. They are non-interfering. It's a slightly complex matching world. So tags are an old feature of MPI. Sometimes tags get abused also. Tags are used to convey additional information like a termination bit. I am done can be encoded in a tag. Anyway, it's in any tag, so there is not much. Okay, so coming back, I receive, num receive plus plus. You can get the status. Who is the sender? You can find that out by taking the status descriptor out of the. See, I put it on a steel plate and it went away. I think status descriptor from the receive and find out who sent me something. I can find that out. That's a nice feature. No, it's not. My theory is wrong. It's, somehow I had to ground myself or something. I don't know. Okay, then okay, num sent. Okay, I think you get the idea in a certain sense. So where is this else going? If num sends less than a rows. Okay, so did I send all the rows of A? I think that's what it's saying. Else send. There is a cycling of additional sends. So this big else goes with this bcast. So this bcast is broadcast to the B matrix. sorry. So there is a, these are all the other processes, I think. Yeah. So these are all the other processes which are going to be the worker processes, and the worker processes are going to happily compute, and maybe the battery, because you have an afternoon worth of real fun lectures from NVIDIA, and you eat also. So anyway, so I'll get the code structure conveyed. So this uses very few collectives, and mostly it is send receive, but this bcast is to receive the B matrix. So this is the receiver's part. It receives a row. It receives a row, and now this is the way for the master to tell no more rows. Okay, so the master knows that all the rows have been sent. It sends through the tag lane as 0. This is an interesting style. I have seen it in some code. Then it breaks out and finalizes. Otherwise, it knows which row it is, and then it does the multiplication, then sends back the answer. It's pretty indicative of the communication here, the rotate more, send more work, get the work done. Let us look at matrix multiply 4. This is what a very capable MPA programmer might do, and I'll take a few minutes just to show the code pattern. We don't need to understand everything. So this is a version that tries to use iSend and iReceive and tries to delay the operations in a software pipeline, which makes the overlap maximum, etc. And then it cycles work to whoever finishes first. So that's the reflection I have. So my ID equal to master, create the matrices, broadcast the B matrix, then send the row. This is I think this is an important construct you need to know. This is a good pattern to know because it appears a lot. So usually iSend is a very nice construct. iSend says start the send, and I told that the wait operation can come much later than you put MPI wait. But there is a very nice variation saying you can do a whole bunch of iSends and then do a wait all. So the whole bunch of sends can be started, they can be flying around, they can be completing with other operations, then say wait all. Wait all has some variations, wait all, wait some, wait any. I don't get into it, but wait all is a good closure, saying has everything I started finished. So this is an optimized code which does wait all on multiple messages. Then what are the other optimizations it has? This is the other optimization. After having sent all the work, the master saying, did anybody finish? So who finished it? And if anybody answers with a receive from any source, I know I got a message from somebody, then I'll find out who finished it, and then I will send to that process a message as I remember. Sender equal to status. Okay, here, there it is. See? So I discover who sent me the first answer. Bright student answered a question, says, here, I got my answer. Okay, bright kid, you get more work. So the sender is the bright kid who says, here's my answer. So you punish the bright kid by sending him more work. Okay, that's more work for you. That's what it is doing. So this is opportunistically trying to send more work to whoever finishes first. And their wildcards are useful because so best policies don't answer, then you don't get more work. Okay, but processes don't do that. But this is a good code where, but the real nice thing is, I hope it's nice because MPI send. Where is its weight? That's the So you shift the weight as much around the loop as you can. I think somewhere I need to search for its weight. So you can delay the weight around the loop as late as you can. You can do such things. So you will not see the weight right there. We'll look at the picture to see where it is. Okay. So this guy has to have a weight, otherwise you will. Where is it? Oh yeah, good. Thank you. Aha! This weight is the going around weight. This send started. Before I send again, I need to wait for the previous send to have completed. So this is called software pipelining. You start something, go an entire loop iteration, the wait before you send again. Good eye. That's what it is. So let's confirm that that's the line. Okay. So escape X, display. How many of you are Emacs users here, just for fun? You're Emacs user. Good. Who else? Okay. Emacs is okay. You're also. I started using Emacs when I went to the US in 1981, and it became so addictive. It's a really. I mean, VI is also good, but I cannot work on shell without Emacs. So shell is inside Emacs. Everything. Okay. So and even Git. How many of you are? This is not a contest or anything. How many of you are Git users? Git. Git is a technology that's hard to learn. I put off multiple years, but last year around I started using Git version control, and then I cannot go back to SVN. Do you all use SVN or some version control? I hope. Yeah. Version control is important. It depends on your scale of projects. So even for personal work, I'm using Git. The nice thing is that you can do a lot of edits when you're traveling in a plane or a train, no internet. You come down, then you do a Git pull, others commits come in, and you can do push. Git, all right. Okay, so this is exactly what it is. So there is an MPI weight associated at line 96, and there is a MPI ISENT at 98. So let us look at the pictures for this one. This is not it. So let us look at and Chris Wood's tutorials are very good. I gave you the Chris Wood's tutorials. He teaches you Git very well. So I'm going to look at 96 and 98 to see where the weights are. There is a weight all which we saw. Where is the weight? Is this the right? Oh, 1 of 18. I don't know. I thought that, there is a weight. No, that's not that weight. I don't know where this weight is. I was expecting that weight to be logged, but this is puzzling. I'll have to see why the weight was not recorded, or was the matrix too small or something. That could be it. If the number of rows supplied is not sufficient, I can test that theory by running a bigger session in a second. If it didn't have more work to cycle, then I shouldn't see the weight. That's my theory. Otherwise, there's something wrong with the tool. But anyway, that's the idea. So I think this code gave some indications of what else could be done. The idea is that you can use ISEND and wait all, and then you can use probe like before, then you can use software pipelining to delay the waits. So I just wanted to see whether I can test my theory that if the matrix size is increased, it'll show the weights. Okay, so ISP CC MPI so let us invent some ISP, but these matrices are already small. I think I need to edit this. I think that's why, because yeah, I don't want to reduce the number of ranks to be too small. That is one way to make the matrices relatively big, but that's not what I want. So let us resize the matrices and see max A rows, max A columns, and then define. Okay, so I'll increase the max A rows to. So this is doing a 4 by 8 and 8 by 4. So it's doing a 4 by 8 and 8 by 4. Okay, so that should be consistent. It'll run a lot of interleaving, sorry about that, because since it's the first finisher who gets more work, the non-deterministic match will consider every possible first finisher. This is going to be ridiculous. It is going to multiply the two matrices so many times over and over again. That's what a testing tool like this sometimes does. But we don't know how to suppress it. I don't know why the abort happened. I hope that's not bad. Core also dumped. Okay, that's not a good sign. Okay. Should I look at the log? So I called it big log. Move/temp big log to there. Let us see what is contained in the log, and then we'll exit. We may get a bug to look at, but that will be the last showpiece if it happens. So SCP Ganesh. I can see the eyelids droop. That means the class was a success. or you're hungry. Okay. We all see it as teachers, right? Okay, it came back. It's a big log. It's a very big log, unfortunately. But I just wanted to see if the weight happens. No, I don't see the weights happen. Sorry, I need to. Huh? Weight all is there. That is for the initial send. But then when the work gets cycled, Oh, there is a weight. That's. Oh, is that happening? I don't know. Is this the right line number? 96. Which weight is it? 96 is there, and 96 weight is. Yeah, you are sort of right. Yeah, so that weight is getting picked up. I maybe didn't see it. So it's cycling the work. So this is 96, and let us look at the 98 should be the I-send, matching I-send. So sometimes the weight matching the 98, 96. Yeah. So the matching weight can be before you. Okay, that's fine. That's because in the code path it is coming around the loop. Yeah. Okay, well, I hope at least the taste of MPA has been imparted, and we saw briefly how MPA plus OpenMP can be somehow fitted into a simple example. We went through the OpenMP, winding back the stack. We looked at other issues and all that. I'm not done. Sorry. Bad news is I have to talk to you tomorrow again. They're getting my money for the money's worth. I'm here, I'm eating, so I have to do this. But tomorrow, I think it will be threading building blocks. Oh, sorry, I opted. I'm talking live anyway, thanks. So tomorrow I'll be talking about threading building blocks, TBB. I hope to do pi and things like that, but the nice thing in TBB is you'll see automatic chunking. You saw in OpenMP that the chunk size that we decided. So TBB, it actually dynamically figures out the best chunk size and defines the work to cores. So there'll be some good visuals to see TBB. Then I'll talk about some higher level frameworks. That will be my job tomorrow. Today afternoon, nothing more for me. So enjoy your lunch. I'll see you there.